Dr. Martin, would you like to introduce your student?
Oh, yeah. Hi, everyone. This is John Graffeo, a master's student in the Chemistry and Geosciences Department, GIST master's student, and he's going to present some of the research we've been working on in coordination with the Alabama Trails Foundation. Yeah, it's cool stuff, so I'll let him tell you all about it.
I'm John Graffeo, a GRA with the Trail Science Institute, and like Dr. Martin said, for about 2 years I've been working with the Alabama Trails Foundation, specifically working with them to do data collection on the Pinhoti National Recreation Trail here in eastern Alabama. Lately our focus has been on brush overgrowth, so areas of the trail where vegetation has encroached the trail, impacting the user experience. Land managers, in this case the Forest Service and then the Trail Foundation, are required to perform maintenance on the trail in order to maintain that National Recreation Trail designation. They get certain amounts of support from the government with that designation. So it's important to them to maintain the trail not only for users, but so that they can continue receiving that support. And part of that work is knowing where to go. So myself and other research assistants, we spend a good deal of time walking the trail and cataloging a lot of information. Specific to this project is just the brush survey. So we're looking at the species makeup of vegetation overgrowth, the linear extent of the overgrowth, and general trail conditions. And that's kind of where this project has stemmed from. So here I am focusing on a remote sensing workflow to be integrated into the vegetation maintenance planning structure, generally, hopefully earlier on in that process. This is a workflow that can be done remotely and will maybe, hopefully, eliminate the need for the Trail Foundation or the Forest Service to pay individuals to go and survey some of these areas. So the goal is to just make the planning process a little more efficient of time and resources. So this project is focused in eastern Alabama. Our study site specifically is a little east of Talladega, near Gunthertown. This is on section 5 of the Pinhoti Trail. Section 5 is about 13.5 miles, a little east of Talladega, in the Talladega Ranger District. So our national forest to the east is broken down into Shoal Creek and Talladega Ranger Districts. And Talladega is this brown polygon down here with Shoal Creek to the northeast. And then this star is where all this data is. So this workflow uses airborne LiDAR data. LiDAR is light detection and ranging. This is an active remote sensing method where a sensor on an either a fixed wing drone, an airplane, or a smaller unmanned aircraft like a quadcopter or something that our department uses, has a sensor on it that sends lasers down, and those lasers come into contact with objects and then return to the sensor. They give us both vertical and horizontal information, which makes LiDAR really useful for modeling tree canopy and forest structure. And that's how it's being used in the context of this project as well. So first portion of the project is I'm taking some point clouds that I sourced from the USGS. This data is freely available. And that is the left side of this graphic, this nice colorful square. This is a point cloud. So this is just a collection of those laser returns. Using this data, I'm classifying it into the first and last returns, effectively showing in forested areas the very top of the forest canopy, and then as the first return, and then the last return being the bare earth. So you subtract the bare earth height values from the top of the canopy values, and you effectively get canopy height or tree height. It is not, it's kind of a misleading name because it's not the height of an individual tree necessarily. When you look on either the right side of this graphic or the one below it, you can see it kind of just looks like an image of the top of a forest, right? And so those values are not on a per tree basis, it's on a return basis. So it more approximates canopy coverage in this case. And in this brown and green graphic here, the green values being higher and the brown values being lower, closer to the ground. And my goal in doing this was trying to find gaps in the tree canopy, because my time in the field, I noticed that a lot of the more severe overgrowth occurs in areas where there is little to no tree cover. What that does is it influences the available resources to understory vegetation. Generally, that understory vegetation would be in more strict competition with each other, and they'd be quite a lot more limited in where they can grow and how quickly they can grow. When you take that tree canopy away, those resources are more plentiful, and that vegetation can grow rapidly, especially during summer months. The data I used from the USGS was taken in July 2020, so well into the growing season and relatively recent, which is great because we don't actually have a lot of control over the time frames of this data, since it's just supplied federally and for free. With that canopy height model, what I wanted to find was the range of canopy heights where that vegetation overgrowth existed. And so to do that, I'm using data that I took from the brush survey, specifically the polyline data, which polylines, it's just, in a GIS, it's just a line feature. It is a collection of vertices that are strung together to resemble a line. And I use these polylines to create a new point feature to use in a point sampling analysis. So the point sampling analysis is just taking XY coordinate pairs and overlaying it on the canopy height layer I've made, and just finding the canopy height value at each coordinate pair and exporting it into a table where I can look at it visually or use it to make graphs, etc. And so that's just this process here. This is going from the original line to a point feature that is just all the vertices that made up the line feature, and then overlaying those points on the canopy height layer and extracting those canopy height values. And those values can be seen here. With the bulk of them existing between 0 and about 15 feet, a little shy of 15 feet. So that kind of just gives us a target range when we're working remotely. So with that range of 0 to specifically it's 12.4 feet, I can extract that range from the original canopy height layer to result in just what we call a mask layer. So this feature, this layer here, is just including the canopy heights of that relevant range and overlaying the original trail line on it, and then also the original brush overgrowth line. So this is kind of the end result of that workflow. The goal is to just have this as a usable layer that can be integrated into the planning efforts. Ideally, you would have this on a section-wide or even trail-wide basis, where you can just take your layer of canopy heights where you can find this vegetation overgrowth, and then you can take your trail line and look for areas with intersects, such as this area right here. This area in particular was pretty rough on the ground. There's quite a lot of overgrowth there. This is an area that I was in person, which is why I chose this as the first site. But from a management standpoint, this is a really quick way to evaluate where you might want to focus your initial efforts, which is the goal here, because you can do this in other areas with just having the trail line data, which is readily available for the Trail Foundation and the Forest Service. And then these LiDAR point clouds, which for pretty much all of eastern Alabama is equally available. And that is pretty much the extent of the project as of now. There are some pretty interesting angles to take this for further research or future graduate research assistants. One area I'd like to see it expanded into is testing the efficacy of this process in different forest types. So this example here is kind of a mixed forest stand. It was oak dominant with some pines in there as well. But the dynamics of resource competition are different in different forest types. So I'd be curious to see maybe a statistical analysis between this process applied to different forest landscapes, something like that.
Are there questions for our speaker?
Can you zoom out? Yeah, zoom out so we can see the whole poster.
Yeah, I was wondering, can you use this data to monitor change over time, and would that be informative or useful? Or, in other words, what I'm wondering is, like, once whoever was using this data kind of got a handle on how things were sort of encroaching, would that just sort of provide them with a prediction for, well, this time of year we need to get out there, or is it something that you would need to monitor yearly because it's going to be different every year?
I would say that is going to depend on first scale. If I were just interested in this small area, it would be completely reasonable to have like a really fine temporal scale, because it's a pretty small area. It'd be easy if you had access to just your own drone and a LiDAR sensor, or the ability to contract someone with their own. This is, a day of work a year if you were only interested in one time a year. That you could go and collect that data and look at a much finer scale. For the data that I'm using, we have very little control over when they fly and collect this data. We're pretty much just, just lucky to use it, really. So scale's really important there. And then I guess just your motivations, because for management, they're well aware of a lot of these dynamics, especially when it's understory. As long as they know the species, they can kind of predict if that's going to be an annual revisit. They don't necessarily need to rerun the process every year if they know that the species are just grasses and grass-likes. They know just that that's going to shoot up in the spring and summer, and they're just going to send someone out there to do a mechanical treatment. So management goals are also going to influence that a little bit, I think. But I think the opportunity is there to either do this every couple years or every year. I think it really depends on the goals and the scale.
All right, let's thank our speaker again.